Okay, so let's learn about some vectors and scalars here, and then we'll learn how to do some basic vector addition. So you have seen vectors and scalars before. I'm just going to remind you as to what they are. So a vector is a measure or value which has both magnitude, so size, and direction. And vectors can be represented in a few different ways. So you might see vector as like an arrow. Okay, and the size of the arrow indicates the magnitude, so how big it is, and the direction the arrow is pointing indicates which way the vector points, right? And you could have any of these. Now, usually they're not just like that. Usually what you'll see is a value, like 5 meters, or 3 meters per second, okay, or so on. Okay, so it's showing you a direction, and then the magnitude is shown by the size of the arrow or by a number value. Okay. You can also, you might also run into vectors that are indicated where their direction is indicated by a negative or a positive sign. So where you'd see something like that is, let's say you have a number line, okay, and you're talking about, this may be representing an object or a person moving along a number line, okay? So we say that this is the 0 point, this represents their house or something like that. You might have someone walking along the number line this way, say, okay? So in this case, we might say if they went from, what is this, -4 to 5 here, the distance they walked here would be +9, or 9 meters. However, if the person walked, say, from here to here, so from 6 to 3, you might say that they walked -3 meters. So in this case, we're showing the direction that they're walking using a negative and positive sign. All right? So in some cases, it's sensible to draw your vector with an arrow. In some cases, it's sensible to use a negative or a positive sign. Okay, when we get into what's called kinematics, we'll be using the negative and positives a lot more. When we do vector addition, we'll be using the arrow method a lot more. Okay, so the question is, what sorts of things are vectors? Oops, it's probably not a C point. So things that are vectors that we'll see in physics. Can anyone give me some examples? Things that you know already are vectors? Well, one famous one would be displacement, which is change in position. And in words, vectors are often just like this. So for example, you might get 5 meters east. That's a vector. It has a magnitude and a direction, right? Or -5 meters, depending on context, if you're talking about something like this, right? This guy's displacement from his original position is -3 meters. He's 3 to the left from where he was. He's 3. Okay. Or you could even draw something like this. So this is the east direction, and there's 5 meters. Oops, I put negative. Usually we call east positive, so my mistake. If it was, say, 5 meters west, then we might see -5 meters, okay? And we might have that. Okay, so we indicate direction in some way. We would never put -5 and the arrow, because the arrow is showing you the -5. And we would never put the arrow and west. It's unnecessary, okay? So it's just one or the other, all right? So all of these represent the same thing. All these represent the same thing. So that's vector, displacement. Any value that you get that has a vector value input ends up being a vector as well. So in this case, velocity would be an example of that. So velocity is found as your displacement, which we often write as delta d over time. Okay? Time is not a vector value, it's a scalar value, but displacement is, okay? And therefore, the value you get from it, velocity, is also a vector value. So that's something to remember. So write a little note. If a value is found by, or defined even, by using a vector input, that value is a vector. Okay, so velocity is a vector. And then one step higher, and this I'm just dealing with stuff that you've already sort of studied, right? Acceleration. Well, that's found as a change in velocity with time, right? So it also would be a vector value. Okay, so the direction that you're traveling, and the direction of your acceleration, and the direction of your displacement are all important parts of understanding how objects move. And that's what we're kind of getting towards here, right? We're going to study how objects move. Direction is a very important part of that. In everyday life, we often don't really use vectors in the same way. And I'll talk about that in just a minute. Before we do, I just want to list off a few more vectors that we will talk about, but that you maybe haven't seen yet or haven't seen very much. So force is a vector. Weight is a vector. And that's actually probably good for now, really. These are values that we're going to be using very frequently through the next few weeks, okay? And then scalar values. These are kind of the more familiar, like everyday versions of these guys, like speed, right? If you say you're driving your car 100 kilometers per hour, your speedometer is going to show you that value regardless of what direction you're pointing your car, right? So speed is independent of direction. Okay? Distance, same idea. You can go for a walk, right? And your distance just is how much ground you covered. It doesn't talk really about whether you went in circles or whether you went straight out and back or whether you just walked from point A to point B. How much ground you covered. Okay, mass. Mass doesn't have a direction. It's just, you know, a measure of the amount of matter in a place, right? Time. Time only moves in one direction, right? It only moves forward. So to talk about negative time doesn't really make a lot of sense. Well, I guess you could maybe argue that the time before something starts is negative time, but it's not really the way we tend to use time. So it's not considered to be a vector value. Okay, just going back up, sometimes to avoid confusion, if people are talking about d here and they want to make sure you understand that we mean displacement, not distance, you might see like a little arrow drawn over top. Depending on who's doing the notation, you might see that. All that means is that we're talking about a vector value, okay? So in some physics books and so on, you might see a little arrow over top. It's not necessary to draw it. I think the expectation is that you are in tune enough with the problems that you're doing that you get whether or not you're dealing with vectors or scalars. You have to understand what you're doing. Just relying on whether there's an arrow on top of here or not probably means you're tending to space monkey a little bit, okay? But I guess in certain situations, drawing this little arrow on here might be important. I don't really ever bother. Just expect that you know whether we're dealing with vector values or not, so just be aware of that. Are there any questions so far? Okay, so this is, I think, essentially a review. You would have studied this in grade 10. Here we're going to get into the new stuff, okay? So the first thing we're going to talk about is vector addition. Okay, and we're going to talk about it in a fairly simple way first. It gets slightly more complex after that. So we'll start with just a simple number line question here, okay? So a number line, and of course I'm assuming that you've dealt with number lines in the past when talking about motion. It's a good way to visualize how something is moving. Okay, and let's imagine that, you know, at time A, this person is in position A, and then they move to position B here. Okay, so we're going to say that this is vector A, and it is 1, 2, 3. Okay, now how did I get 3 from there? Well, I get 3 because I know that the difference between B and A is 3. So this introduces some new nomenclature that we're just going to make sure that you guys have in place. So let's just see where this is. So -1, -2, -3, -4, -5. So how do I get 3 from a -5 and a -2? Well, what I'm saying here is I am looking at the change in position of this person, right? I want to know about the change in position. Essentially how far they moved and what direction. So really that we have a name for that value, and that's the displacement. We sort of talked about it before. But displacement is found as the change in position. Now change in position is shown in physics by a delta sign. Okay? So we call displacement here delta position. So how my position has changed. And the way you calculate a delta is you simply say what it is it's the final position, P final, minus P initial. Okay, so let's see if that works out to give us 3 here, right? So the displacement, we're going to call delta D, is your final position minus your initial. So your final position here is -2, and you're going to subtract the initial position from that, minus -5. So -2 minus -5 is the same as saying -2 plus 5. -2 plus 5 is 3, right? So you have to be able to add and subtract your negatives and positives. So hopefully that works out for you. So -5 minus, sorry, -2 minus -5. Okay, so moving along. So this creates a vector, right? This creates a vector, and that vector is 3 meters, and it's in the positive direction, and we're sort of indicating that with this arrow. Now, let's say the person moves again over to here. All right, so now they're at 1, 2, 3, 4, position 4, and they started at -2, so their delta D is their final minus their initial, so we have 4 minus -2, so they've now gone 6 meters. So the new vector we have here is 6 meters, all right? We'll call this position C. Position C. So we have 2 vectors here, and if we want to look at their total trip, what we would do is we would add these 2 vectors together. They have gone 9 meters, from -5 to +4. That's 9 meters. So if I lay it all out to you like this, it's fairly obvious as to what's going on, and they're always moving in the positive direction. But what I could say to you is I could say add 3 meters, or actually, sorry, that's not a good way to say it. This is how you would probably see it in just words, okay? A person starts at -5 meters, travels 3 meters to the right, followed by 6 meters to the right. You say calculate the displacement and find their final position, PF. Okay, so you might get something like that just in words. Now, if you just saw that, it might be a little bit difficult to just immediately wrap your mind around what this is asking you to do. So, what do? You draw yourself a little picture to help guide you. especially for the first 5 or 6 of these that you end up having to do, it just is going to help you make sure that your brain's wrapped. Now, there's a rule here, okay? So what we're going to do here is we're going to do adding vectors, or better yet, vector addition. Okay, and this is 2D vector addition. You just have essentially just 2 dimensions. Actually, it's sort of 1D. You can only go back and forth along the line. Later, we'll talk about vectors where you go in 2 different directions and see what happens there. So there's a rule for adding vectors that you have to always remember. And that is that vectors are added tip to tail. Okay? Vectors are added tip to tail. So what does that mean? What that means is we're going to take our first vector, which was 3 meters, and the tip of it is going to attach to the tail of the next vector, which was 6 meters. And we're simply going to add them up. So what do we get here? Well, we get a total vector equal to 9 meters to the right in the positive direction. Okay, so that solves part A. Our total displacement here is the sum of these 2 vectors. Makes sense? And then the next thing we were asked is, well, what's the final position? We already know because we drew a picture, but let's see how we would do it just using, math symbols. So we know this, right? We know delta D, the displacement, is equal to the final minus the initial position. So this information here tells you the person starts at -5, but it doesn't say where they end, right? So where they end in this place is PF. Okay, this is what we want. We want to know this. We want that. Okay, we know their initial position was -3, and we've just sorted out through vector addition that their total displacement, or their change in position, was 9 meters. So we're going to solve for this. So what we're going to do is take this formula and rearrange so that we isolate PF. So PF would be found if we take delta D and we add PI to it, plus PI. So what do we get? PF should be found with 9 meters plus -3 . And if you do this, 9 plus -3, 9, 8, 7, 6, we should be at 6 meters, and that is the final position that we predict this person will be at. And they're not. Why not? Oh, of course, that's why. Silly guy. Use the right numbers and that will help. Thanks, guys. Easy to fix. And that makes that 4 meters, like we would expect. Oopsies. All right, let's do one more example here. We'll do this without a number line at first. Okay, so you walk 10 meters east, followed by 7 meters west. Okay? If you started 17 meters to the east of your house, A, what is your displacement? So that's a measure from where you started. And B, your final position. Just something a little bit different. So let's do this one in reverse order. Let's use our math first, and then our and then we'll draw a picture. So you walk 10 meters east. So I'd recommend let's draw that vector. There's to the east, and there's 10 meters. Followed by 7 meters to the west. So you walk here, and then you walk 7 meters to the west. Okay, so this is a vector addition. If we do one vector after another, we add them tip to tail. So if we add these guys tip to tail, we get 10 meters this way, and we get 7 meters this way. And then if this is our start and this is our finish, right, this represents our delta D, our change in position. So if I look, I went 10 meters plus -7. So where am I? I am at 3 meters to the right of where I was before, 3 meters to the east of where I was before. Make sense? Okay. So that's our kind of just our graphical tip to tail mathematical adding. Okay. And really what we're doing is we're just saying 10 plus -7 equals 3 meters, right? This represents -7, that equals 3 meters. Okay, so this is our overall displacement. And now the second thing said, you started at, so initial position in this case was 17 meters to the east, okay? And you know that your delta D was 3 meters, and you need to find your final position. So our math said delta D is equal to final minus initial, and we want this guy. So we're going to say then that the final position should be equal to the change in position plus initial position. So 3 meters plus initial 17 meters. You should be at 20 meters. All right, let's prove it by drawing a picture. So quick picture, just to verify that what we said is right. Okay, so, you know, zero's over here somewhere. Let's say here's 15, 16, 17, 18, 19, 20, 1, 2, 3. $27. Okay, so you start here, initial position. You go 10 to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you get all the way over to 27. There's your first vector. Okay, then you go 7 to the west. 1, 2, 7 to the west. Now we're back here, the magic position that we said we were at, and everything works out. Okay, so we've checked our work. Life's good. Bob's your uncle. Okay? Now the second thing we could ask, which we will later, I'm not going to go into this right now, is if you know how long this took, find your speed, which is the total distance you covered, and the velocity, which just takes into account the difference, right? That 3 meters difference. So I would just give you time and ask you these two questions, and you'd have to figure that out. But that's for later. Okay, right now we're just focusing on the adding and subtracting of vectors. Okay, so let's step it up a notch. You walk 5 meters north, then 10 meters east. Find your displacement. Uh-oh. So now we've got something new, okay? Now we've got a new dimension put in here. Luckily, this is going to be fairly easy for you to deal with. So you went 5 meters north, and then you went 10 meters east, right? So how far in total did you walk? Well, you walked 15 meters, right? But what we want to know is what is your displacement? So displacement means how far out of place you are. And we know it's a vector, so it's also going to include a direction. So your displacement is actually going to be this, right? The reason being is because this is your start point, your initial point, and this is your final position. Now notice what I did, and it just naturally flows from the way the problem was laid out. I added these vectors tip to tail. Here is the tip of my first vector added to the tail of the next vector, okay? Sometimes people do things wrong, like they might go tip to tip, like they might go this and then that. Well, that's not going to work, right? That's going to tell you your displacement is like down here somewhere, which clearly is not the right way. So if you just remember always tip to tail, tip to tail, tip to tail, life's good. Okay? If you start to improvise and make up your own methods, you're going to have a bad time. So how would you go about solving this? Well, there's a couple of things you need to think about. First of all, this direction is not a cardinal direction. It's not northeast, south, or west. It's some measured value away from north, or if you want, some measured value away from east. If that's east and that's north, this angle is some value theta, or some value, if you want alpha, doesn't really matter what symbol we use, measured away from your cardinal direction. And then the size of it, you're going to have to find using, well, your right angle triangle rules, right? So let's figure this out. So first, let's find the magnitude. Well, magnitude is going to be found using some stuff from math, and that's Pythagorean theorem, right? Finding the C side of a right angle triangle, A, B, and C. So we say, well, we know C squared equals A squared plus B squared, or C, the value we're looking for, should be equal to the root of A squared plus B squared. In this case, that's 5 squared plus 10 squared, and root it up. So 11.2 meters. Okay? And then the other part of this is our displacement isn't 11.2. The distance from where we started is 11.2, okay? But we need the angle as well. So in this case, we have the opposite and the adjacent, right? And we know from math class that the tan of theta should be equal to the opposite, O, over the adjacent, A. Or in this case, 10/5, okay? Now we want theta, so we're going to have to inverse tan that guy. So theta equals the inverted tan of 10/5. So we need to solve that. And make sure your calculator is in degree and not radian mode if you're taking radians in math class, because that will not give you a satisfactory answer in degrees if you have it in radian modes. Okay, so we get 63 degrees, roughly. So 63 degrees is this value right here. Now what do we say? We say that is 63 degrees towards the east from north, or east of north. Okay, so north is our cardinal direction, and that is towards the east from north, right? We know this. Never eat soggy wieners. Right, to the east from north. We're measuring towards east from north. People have trouble with this all the time, east of north. So I would write my final answer like this, sort of, my quasi-final answer. I'd write, I have a displacement now of 11.2 meters, 63 degrees east of north. Now, is there another way to measure this angle than 63 degrees east of north? Could I not measure this angle from the east? What if this is 63, what value would this have? 27 degrees. Now there's a rule of thumb. This is not wrong. This is fine. But the rule of thumb says you should always go for, if you're dealing with cardinal directions, the value that is the smaller of the two possibilities. So one will, unless this is 45 degrees, one value will be larger than the other, right? The rule of thumb is go with the smaller one. So the absolute correct full marks answer for this is 27 degrees towards the north from east, right? So we're going, here's east, and we're going back towards the north, okay? So 27 degrees north of east, okay? This concept is basic vector addition, okay? And it's really as simple as that. Put your vectors tip to tail, and life's good. Okay? Any other questions? Just before we leave this, there'll be another video showing how to deal with this later. But what if you wanted to do subtraction of vectors? Well, it's kind of like this. What if you wanted to go 5 minus 2 in math? Well, you go 5, 4, 3. But another way to do that is you could say, let's make this 5 plus negative 2. So what we're saying is instead of subtracting 2 away, we're going to add a negative 2 to it, right? We can do that. This makes sense to us. So with vectors, we're going to take this approach. We're going to add the opposite vector. Okay? I'll just do a tiny example. We won't actually solve it, but just so you know what I mean. Example. Subtract 5 meters east from 10 meters north. So what we want to say then is we want to say, okay, so I've got 10 meters north minus 5 meters east, right? That's what we want, 10 meters north minus 5 meters east. We're going to say that's the same as saying 10 meters north plus what's the opposite of 5 meters east? Yeah. And there we go, and we're just going to do this. And this resulting value here, this is 10 meters, this is 5 meters. This is the subtraction of those two. Okay, so we're just adding the opposite. So if you're asked to subtract vectors, you just simply add the opposite value, just like you would do in math class. And that's the end of that.